So for this last video, we're going to be switching gears a little bit, where we won't be thinking about things so much in a different 3D spatial setting, but we're going to be looking at molecules in a slightly different way. So what we're going to talk about next is something called Fischer projections. And these are typically used in a biological setting, right, for a lot of sugars, essentially. But this is going to be super important to talk about, especially for those of you who are going on to a more bio-related field. So Fischer projections are a convention to look at molecules in a slightly different way where everything is totally flat. And so the convention typically is horizontal lines coming out of the plane, right, wedged, and vertical lines going into the plane, dashed. So what do we mean by that? So in a typical Fischer projection, I'm going to zoom in here a little bit, we have something like this, where we have bonds that are totally flat, okay? And what we have to do is when we draw in the different atoms, we have to draw them appropriately on the bonds. So I'm just giving a crude example here that we're going to go through, okay? And so, right, remembering our conventions, horizontal lines, right, this is a horizontal line, are coming out of the plane, and vertical lines are going into the plane, okay? So this is what a Fischer projection looks like, right here. Right? And when we want to start working through this problem, we have to think about them in the convention that they're meant to, okay? So taking this, right, and remembering that horizontal lines are coming out of the plane, right, so I'm going to turn this into a wedge, and vertical lines are going into the plane, right, so these bonds are on dashes, right? And so now this tetrahedral carbon in the center still has those bonds 109.5 degrees apart, right? It's hard to tell here because everything looks like it's 90 degrees, but this is what it looks like in a bond line fashion, or a line angle fashion rather, right, with wedges and dashes. So what we have to do, right, to orient this back into a familiar setting for us is we have to sort of turn it, okay? Turn it and point it towards us. And so what we can do with that, right, is start with something like this, right, as our framework, right, with our central carbon here, right, and we know we have a, right, on a tetrahedral carbon, we know we have a wedged bond and a dashed bond, right, so looking at the structure, right, we're essentially twisting it towards ourselves, right, and so what happens when we do that is we have our OH at the top, down here, CH3 on the other end, because we turn this totally towards ourselves, these dash bonds are going to be in the plane. We're going to have one bond that's wedged, right, so that'll be our bromine, and the chlorine back here, because we're pointing this molecule toward ourselves, it's going away from us. So it's dashed, right? And so the way to think about this, that might just be the easiest to sort of remember, is looking at this Fischer projection up top. All bonds toward the right are on wedges, and all bonds to the left are on dashes. Okay, so bromine, right, it's on the right, so it's on a dash. And chlorine, or sorry, bromine's on a wedge, right, because it's pointing towards the right. And chlorine, pointing to the left, is on a dash bond. Okay, so when you see something like this, you can just simply convert it right away by following this little trick here. And we'll go through some more of these examples to sort of get a little better at doing that. So what about converting a molecule to a Fischer projection, right, rather than going from a Fischer projection to a molecule? So what we have to do here, right, remembering the convention, right, we need to have the molecules here that are on wedges and dashes in the horizontal plane, and the molecules that are in the plane should be vertical, right? So So essentially what we're doing here is we are twisting this molecule this way. Right? We're taking it and rotating it in the direction of the arrow. So we end up with something like this. The hydrogen and the OH, right, are pointing towards us. And now this aldehyde and this methyl alcohol, this methyl alcohol is pointing away from us, right? And so now we can just simply convert this to a Fischer projection, right? Making sure we keep things sort of the same here, right? So we have to sort of flip this around. Right, we're just rotating it on the side to keep things consistent. And then finally, we end up with our Fischer projection. And so when you're converting back to a line angle structure, what you can do is, right, now that we know how to name chiral centers, we can go ahead and assign chirality to this back in line angle structure, right? If you ever have to convert from bond line to Fischer and then back again, you're not sure if the molecule is the same or not, just look at the chiral center and name it RS, and you'll be able to determine if you drew it back correctly or not. So that's pretty much it for Fischer projections. We'll go through some more examples in lecture to sort of get a hang of it, because it's sort of a weird angle to look at molecules. But before we end the chapter, what I want to just like sort of quickly go over are some other examples of chiral centers, right? Because we've only been seeing carbon so far, and that's pretty much all we'll ever see, unless there's like a really unique example that I'm showing. But right, there are other tetrahedral atoms, right? Ammonium, right? Nitrogen with 4 bonds, positive, but it is a chiral center, right? There is 4 different bonds at 4 different angles where we could get an enantiomer, right, of this molecule. Same with silicon, right? The atom right below carbon has, right, the same tetrahedral geometry. We could have a chiral center here. And more importantly, right, with nitrogen and phosphorus, right, it has a pyramidal geometry. That lone pair can be considered a different group. So we could say that these 2 molecules here, right, are enantiomers. But the issue with that, at least from like a realistic setting, is that the lone pair of nitrogen interconverts rapidly. So it basically kind of goes through the nitrogen and spits out the lone pair at the bottom and flips the whole molecule up, right? All those bonds are now sort of pointing upward. This happens basically at room temperature. And so even though this is an enantiomer, they rapidly convert so fast that there's pretty much no point in sort of considering its chiral nature. Phosphorus is a little bit slower because it's so big, and sometimes bulkier groups makes this interconversion happen a bit slower, right? We can see that through the kcal per mole difference here. It still interconverts. And so, again, sort of pointless, quote unquote, to talk about these atoms, right, these tetrahedral nitrogen phosphorus atoms as chiral centers, right, because they interconvert. All right, so we have a few pages here about doing Fischer projections. So take a look at these if you can, and try to, if there's a Fischer projection, convert it to line angle, and if there's a line angle structure, right, like this here, convert it to a Fischer projection. And we'll go over these in class and try to figure out these sort of weird-looking ways to look at structures.